About using the signal processing capabilities of LabVIEW within Visual Systems Simulator. So over the past year, National Instruments and AWR have been working together to collaborate on connectivity between the LabVIEW environment and the Visual Systems Simulator environment. And this collaboration is sort of a natural transition because in a system-level simulation tool, it turns out that the data types of data passed between blocks like an amplifier and filter can conveniently marry to a programming language or programming environment like LabVIEW. We're effectively talking about arrays of complex doubles. And so this connectivity really allows us to do a couple of things. If you kind of look through the design flow, you can kind of imagine using measurements to help aid research and modeling right here. We're going to talk about that a little bit. We talked a little bit about this earlier today as well. Primarily, we're going to focus the next 10 minutes is using a LabVIEW and some of its signal processing capabilities and measurement capabilities as a tool to do validation and verification of a design. And there's a couple questions. You know, why would we connect LabVIEW and VSS? What's the motivation? LabVIEW is really good at a couple different things. One is signal processing, right? You can create an LTE waveform. You can demodulate an LTE signal. You could create a custom chirp. You can measure the linearity of a chirp using the native signal processing capabilities. And that's pretty useful from an analog system simulation point of view. The other thing that LabVIEW is good at is bringing hardware or controlling hardware with software. So if you, for example, wanted to get an S21 measurement off of a vector network analyzer, it's pretty convenient to do that in LabVIEW. And you can imagine if VSS connects to LabVIEW, it also connects, therefore, to all instruments that LabVIEW connects to. So the ultimate goal is for us to be able to use measurements as part of the simulation process. So just to kind of give you an introduction, when I talk about Visual Systems Simulator, it's a system design tool that allows us to connect various components as part of either a communication system or as an RF system. So here you can see, here's a transmit block, an amplifier block, here's a demodulator block. You could, in fact, design an RF signal analyzer in this particular environment. So if we can contrast that to how an RF signal analyzer works, I think it'll really kind of help drive home how the connectivity really works. So you can imagine you have an RF signal analyzer connected to a device under test like a power amplifier. When you look at that signal analyzer from the front panel, you see a constellation plot, you see a spectrum, maybe an EVM number. But internally, what's going on from a software point of view is that you're simply taking I and Q samples from that signal analyzer, passing it to some demodulation algorithm, and then presenting a result such as a constellation. Effectively, you're passing around arrays of complex data, I and Q, complex doubles. It turns out this analysis block can be used either for a real signal from an analog signal analyzer or from the simulation world from a simulated design such as a power amplifier. So this particular block is hardware specific, but this particular block or series of blocks is highly generic, which means I can create any signal I want and demodulate it using these blocks in LabVIEW. So you can imagine the way that LabVIEW would connect to Visual Systems Simulator is through the time domain circuit envelope simulation engine. So in VSS, here you can see an amplifier, attenuator, mixer. Here's a CW source or local oscillator. And the data type being passed around in the simulation environment is arrays of complex double data. The way the LabVIEW element would connect to this is merely to take the I and Q data and pass it into the same analysis blocks that you would use with hardware. So the way this looks kind of mechanically is that in LabVIEW, you have this notion of controls and indicators, which are sinks and sources to pass data around. These sinks and sources can be called from other programming environments as a subroutine. So you can imagine you have LabVIEW code, you compile it as a DLL. That DLL has a header file, which has a series of inputs and outputs that you can control from another programming environment. You can also think about that in LabVIEW. You create a LabVIEW with controls and indicators. those controls and indicators can be called, or the connection point for other LabVIEW pieces of code to control that. Turns out in the same way, those controls and indicators can also map to ports on the LabVIEW element in VSS. And what this allows you to do is effectively execute this piece of LabVIEW code from the Visual Systems Simulator environment. This particular code does a complex conjugate, but you can do things that are more sophisticated, which we're going to see as we go along. So there you can see the connectivity right there. So one common example, and you can see the demonstration in our booth if you want to, is the simulation versus measured results of a complex device such as a power amplifier. Here you can see I'm using LabVIEW, and I'm using the LTE toolkit in LabVIEW to create an INQ waveform that I can send to another device. Now, in a lot of other environments, this is encrypted, but in LabVIEW, this is fairly open source, which means you can use a LabVIEW toolkit to create a waveform and use that with other generic signal generators, with MATLAB, or whatever else you want. So that INQ waveform goes into a model of a behavioral model of an amplifier, and at the output, we can look at various characteristics of that signal. So in particular, because this is LTE, we would want to demodulate the signal, look at error vector magnitude, probably a constellation plot, and the spectral regrowth as part of an adjacent channel power measurement. And so this is the transmit block. Here's the model of the amplifier, and of course you can see typical metrics that you might observe. Now, a few interesting things about this amplifier. This amplifier was designed in microwave office. Because it's LTE, we'll look at error vector magnitude and adjacent channel power. But because the amplifier was designed within the AWR design environment, we natively have the model for that component within the Visual Systems Simulator world. Now, if we designed that component in a different environment, there's a number of ways that we could also get that model into the VSS world and then do measurements. So now that we've looked at the simulation side, let's look at the measurement side of how we could use these same blocks. So you can imagine if I can create an INQ waveform and pass it to a simulated component, I could certainly pass it to a vector signal generator. So that gives me an analog version of the exact same waveform that I've used to stimulate my simulated model. Of course, my signal generator connects to a signal analyzer. I can take that signal analyzer, and my signal analyzer can acquire INQ waveforms in the same way that my model produces INQ samples. So what that allows me to do is in LabVIEW, I can compare the EVM and ACP of the simulated device with the EVM and ACP of the device under test. This is hardware in the loop. So if we look forward to the next slide, you can see some of the LabVIEW VIs that I would create to implement this. So here's my LabVIEW VI to create a signal. Here's a LabVIEW VI to talk to hardware. So it's going to take INQ waveforms to a signal generator, have a signal analyzer produce the IQ waveform, and then this block is going to do demodulation. Here's actually the block that would connect to hardware, which is that middle one. So there you can see you take the waveform, download it to a signal generator. The signal analyzer just produces INQ waveforms. You can connect anything in between. It doesn't really matter because you can connect it wrap back or an actual device under test. One of the things that I should mention about this technique is that it's also a way to incorporate real components into a simulation. So you can imagine if you're designing an LT or a radar system and you want to model the performance of that radar system at 200 degrees Fahrenheit. 200 degrees Celsius would just be ridiculous. If you did it 200 degrees Fahrenheit, you could very easily put that physical amplifier in a temperature chamber, heat it up to the appropriate temperature, and using this type of connectivity, simulate the system with part of that component operating at the conditions that you would expect in the real world. That's a way that you can use hardware in the loop to have a more accurate system simulation. Of course, we have the amplifier connected here in real life. So at the output, you can observe similar results both on the simulated performance as well as the measured performance. You can see in this particular case, RMS EVM is equivalent, minus 31.5 dB. You see in the measured results, I see slightly asymmetric adjacent channel power, which is indicative, most likely, of memory effects. In this particular simulation, the memory effects that I'm modeling aren't very substantial. In fact, I'm probably not modeling memory effects given that the positive and ACP are the same results. But you can see the physical one is producing the asymmetric memory effects. So this is just one example of how you can use LabVIEW signal processing capabilities within the visual system simulator environment. We should keep in mind that you can do this with any number of signals that LabVIEW can produce or acquire. In this case, we can look at 802.11ac. Here's an example. We're looking at an 80 megahertz bandwidth signal. You can see that it's 256 QAM. In this particular case, we're looking at a simulated EVM of minus 89, well, this would be minus 89 dB, which is a purely simulated or modeled device. Here you can see the 802.11ac blocks within the VSS environment. So here's my LabVIEW as a source. Here's a simulated IF receiver, amplifier, mixer. Here's my IF coming out. And then LabVIEW AC analysis right here. This would be an interesting type of analysis to do if you wanted to look at the effects of the group delay, for example, of this filter on the demodulation or EVM of the particular signal. So just to have a few conclusions, time domain simulation engines can be tightly coupled with LabVIEW's measurement algorithms. And it's really because the data types lend themselves well to interacting with each other. The new feature for VSS code simulation with LabVIEW is, of course, demonstrated in our booth, and you're welcome to stop by and see it. And then, of course, this type of scenario allows you to more tightly correlate simulated measurements, simulation with measurement to see if your simulation is correct or if your measurement is behaving as you would expect. So thanks for joining us, and I guess we'll move on.